Okay, if we take a look, if we take a look at problem number 2 on the homework, 75% of married couples pay for their honeymoon themselves. We only select 20 married couples, so that's your end value. What you need to determine how number of your trials that you have, the number of people you choose. So your n is your total number of whatever you're dealing with here. X is the number of successes that you want, that you're desiring. Okay, so you want to find the probability of that occurring, something occurring. P is your probability for success. Q is the probability for failure or not having success. And how we can calculate this is 1 minus P. Whatever your P is, you take 1 minus that, that's your Q, because you're either going to have this or you're going to have this. Binomial, you have two things. This X is the number of successes, so we have the probability for success to the number of successes. We have the probability of failure. This is number of failures. This NCX will do all your ranging for you. Once again, if you have 5, 4, 3, doesn't matter. You know, you have different arrangements, just like we had different arrangements counting wise up here when we had 3 people, 3 deaths. Okay, and it did not matter what order we're in, so we can have a C because order does not matter. So if we look at problem number 2, if we look at part A and part B of problem number 2, you have to identify each one of these values in each case. Let's see here, 75% of the married couples paid for their honeymoon. You randomly select 20 people. So you have selected 20 people here. 75% paid for their honeymoon. So we have 0.75 for our P. That means Q is 0.25, 1 minus P. In problem A, we want exactly 14. So when we're dealing with exactly 14, that means that is our X value. So I can just substitute in. I have 20, C, 14. P, my probability for success, 0.75, to my number of successes, 14, times the probability of failure, 0.25, to the number of failures. Well, if I have 14 successes, that means 6 of them will be failures. That's where n minus x. Once again, once you get to this point, it is a click-a-clack exercise. You can go to your calculator, you can go to your 20C14. Once again, I have to type in my 20 first. Then we go to our math. Our option 3, 20C14, we're going to multiply that by 0.75 to the 14th power. Whoopsie. To the 14th power times 0.25 to the 6th power. And you can type that all in. One big fail, swoop, shebang. And you come up with your 0.1686. So we have a 16.86% chance that if you choose 20 people at random, if you choose 20 people at random, okay, there's a 16% chance that 14 of them, exactly 14, will say they paid for their honeymoon. Now, if we look at problem B in the same section, it says 15 or more. Okay? Which means we are looking at the probability of 15 or probability of 16 or probability of 17 or probability of 18 or probability of 19 or probability of 20. Because all those are more than 15. 15 or more. 15, 16, 17, 18, 19, 20. Well, if I wanted to, I can run it through this 1, 2, 3, 4, 5, 6 times. That's a lot of work. That's where your book comes in, nice and handy. If you look at your index, when we're dealing with probability and or, we're dealing with addition. So you go back to your index, your appendix. We are looking at the n equals 20. We're looking at that. So you're going to have to flip a couple pages till you get your n equals 20. You have to go to page A10. A10. We have n value of 16 and n value of 20. You have to slide across till you get to your the top row is your p-value. Okay, so we have to go over to our p-value, which we said is 0.75. So we go over to the p-value 0.75, and we take our finger and take it down to our x value of 15, 16, 17, 18, 19, 20. And you want to recopy all those values down. So I can see that you can pull out the right values there. And if you look at 14, 14 came down to what we calculated, the 0.169. Now, on a test, I'm going to give you an exact value or exact problem to do, like this part A, but you will not be able to look it up in your table. I will give you an exact value and a percentage of 0.42 or 0.73, where you're not going to be able to find it in your table. But when I give you a series of them like you have here, I'll give you a multiple of 5, so you can look it up in your table. So when I give you the series one, you can look up on your table because there'll be a multiple 5. When I give you an exact one, it's going to be one that's not a multiple 5, so you will not be able to find it in the table, and you have to use your NCX, PDX, Q to the n minus x. And once again, all I'm asking you to do, we have 0.202, 0.190, 0.134, 0.067, 0.021, and 0.003. And then you'll just have to add these up to get a value.
I got a question.
Yeah.
Why does the table jump like this? Like, why does it go from like 12 to 15 and then from 16 to 20?
Just because there's not enough room in the book for that. You go 15, 16, okay, you go all the way up through 16, and once you get 16, you don't have it for 17, 18, 19, 20. You just didn't have enough room.
Well, I don't have it from 13 or 14 either.
You don't either? No, I'll make sure I have one up 13 and 14. I'll make it so you can work the table when you want to work it. If you go online, you would be able to find binomial probabilities tables online and be able to find that. You're limited to a book. Okay, at the bottom it says calculate the mean standard deviation for the payment of honeymoon costs. So when we talk about the mean and binomial, this is just n times p. Our mean is n times p, so we have 20 times 0.75. So you come down to a value of 15. This is your expected value. So what you would expect, given our data that we have here, what you would expect would be 15 of the 20 people would pay for their honeymoon. That's what you would expect. That's the mean value. Once again, it could be 14, it could be 15, it could be 18. But what you would expect, that's like flipping a coin 10 times. If you flip a coin 10 times, what you would expect, because you have 0.5 for head, 0.5 for tails, you have 0.5 times 10, which is 5 heads and 5 tails. That's what you would expect. And we showed that that's not necessarily going to happen. Standard deviation. Well, first off, your variance is n times p times q. So we have 20 times 0.75 times 0.25. So we can just multiply them out, MPQ. Come down to 3.75 for your variance, and then you can take the square root of that to get your variation. As I've alluded to, this is not a very long chapter. We're going to go through the expected value and the mean idea again today, because there's calculations that could occur with that. The worksheet that you have today, will be very similar to the ideas that we have talked about already. So the topics that we have talked about already, you'll see also on the worksheet today. And the plan, once again, going forward, we'll have a worksheet today. We'll have a worksheet on Monday covering this chapter, review day on Tuesday, quiz on Wednesday, and then we'll have a review day and a unit test over chapter 3 and 4 by the time we leave on spring break next week. At the end of next week. When we talk about an expected value, it's the theoretical. That should be a G in here.
We're not finishing with that semester.
Huh? We did. The last problem, it was just an extra example problem. So me doing what I just did here.
We have the ACT on Wednesday, so should we just come in? You know, something good before that?
Oh, we do?
Yeah.
We'll adjust.
Okay.
We'll adjust.
If you don't have to do it right.
We will adjust. Don't worry.
Alright, you want the
It
next-
ain't my first rodeo. I'll adjust and we'll make it work. Because my ultimate goal is you're gonna have to take it. I'd rather have you take a unit test over what we've just dealt with the last 3 weeks before we go on spring break. Because if not, I'll give it to you Monday when we come back from spring break.
Oh, you wouldn't do that to us. Yeah.
I'd have no problem sleeping. All right?
Yes, you would.
No, I would not.
What if we all bombed it?
I'm an old man.
What if we all bombed it?
Well, that's your grade.
Oh.
I can't, I try to help you and assist you as much as possible in regards to your grades, to give you the best opportunity for you to have success. But ultimately, you have to come my direction too. You have to be able to grab that success. I give you the opportunity to be able to have that.
I'll grab it.
Okay, expected value is the theoretical average of a discrete random variable. Okay, we've talked about that. We have 2 different theoretical averages. Okay, when we were talking about just binomial probability, probability distribution. This was your sum of your x times p of x. Okay, that's what we talked about 2 days ago. Yesterday when we talked about binomial, our theoretical mean is just n times p. Okay, so those are the 2 things that we have talked about in regards to a binomial distribution mean, or just a probability distribution mean. We can add up all the x's times p of x, or we can take n times p when it's a binomial. And when we talk about this expected value, this is the mean. You have sum of x times p of x, or when once again we're talking about a binomial, this is just n times p. We have one problem to go through here, and then I'll give you homework to be able to go start working on this. Just one extra thing to think about here. 500 tickets are sold. Each one costs $1. Okay, 500 tickets sold. Each ticket costs $1. One ticket is drawn and wins $250. What is the expected value of gain? Well, when we're talking about an expected value, we're talking about mean. Okay, setting up like we've done, we have outcome and probability of outcome. Sample space and probability of a sample space. Okay, it's what we've done already. We've set up tables like this. This is an outcome here and the probability of its outcome. Okay, once again, this sets up just what we've talked about already. This is a binomial because what can we do here? We can either win
Or lose.
or lose. We can either win or lose. Hey, there's no maybes here. You're either gonna win or you're gonna lose. Well, you win $250. If you win, if you lose, you don't get the $250.
Right down the drain, because.
Oh well. Easy come, easy go. It's only $1. So if you win, what is your outcome? Hmm?
Oh,
Very good, Matthew. You win, you would win $249. Why? You paid $1 for the ticket. So if you win, you're a plus 249. If you lose,
Plus 251.
no, minus 1. You have minus 1 because you lost $1. What is your probability of winning? How many winning tickets do you have? 1 out of 500. And how many losers are there?
400.
499 out of 500. Well, what we want to deal with here is an expected value, which is a theoretical mean. So we could take the sum of x times p of x. So we have the outcome 249 times 1 out of 500. That is outcome times its probability. Plus a -1 outcome times 499 out of 500. So we have 249 out of 500 plus a -499 out of 500. So when we add these together, we get 250 out of 500. I'm sorry, -250 out of 500. So we have a -0.50 per ticket. Now, what that means is, if you would buy all 500 tickets, you would guarantee you would be winner, winner, chicken dinner. But what the theoretical mean determines and tells us is that for each dollar you spent, you would lose 50 cents. So on every ticket that you bought, you would lose 50 cents. But you'd still gain $250. You say, I won. But you lose $250. So this is what the theoretical mean determines. Let's go to the second scenario. Now the second scenario, I allow a little leeway. First scenario, you bought one ticket. Second scenario, part B,
Thank you,
you bought 2 tickets. We still have outcome and probability of outcome. We still have winner, winner, chicken dinner. And then we still have losers. You now bought 2 tickets. So if you bought 2 tickets, if you win, 248. You have a plus 248 here. If you lose, minus 2. Now comes, I've taught this for like 79 years. Okay? And I still go through this and I have 2 people talking on my shoulders, and that's what happens with me with probabilities. Okay? I'll say one thing, and then all of a sudden, somebody over here will start chirping in my ear also, and try to talk me out of it. What's your probability of of winning? What? You say it because you're going to be right. You're going to be one of my scenarios. Your probability of winning is going to be what? Go ahead.
500.
Huh? 1 out of 500. Now, why would he say 1 out of 500? Well, the question is how many winning tickets will you still have? No, how many winning tickets are there that's going to win $250? Just one. Just one ticket wins $250. But you sit there and go, I just bought 2 tickets. So that should double my chance of getting that winner, winner, chicken dinner. So if you say it's 2 out of 500, because I've doubled my chances, what is your probability of losing? How many losers do we have there? 490. Because one of those tickets that you bought was a winner, winner, chicken dinner, but one of those tickets you bought was a loser.
Okay, but aren't you asking how many, like, you can't have 2 winners, right? But you could be a winner and a loser at the same time.
There we go. So, okay. The scenario that, and once again, this is one, I'm even up here, it's chirping back and forth in my ears right now, okay? Because if you're looking at it as the raffle, if you're looking at it in that direction, the person that has designed the raffle, there's 1 out of 500 tickets that are winners. But if you're looking at the person that shelled out the money and bought the tickets, you're sitting there saying, I have 2 out of 500 chances of winning this. So it depends on how you're looking at it in regards to, if you're looking at it as the raffle, I'm the raffle up here, I'm going to tell you there's 1 ticket that's going to win $250. You're looking at it as the person that bought the tickets, I now have 2 chances to win $250.
Good.
Okay? If you say this is 2 out of 500, what if you lose? What do you have over here? 498 out of 500, or this would be 499 out of 500. One of these 2 ideas, I would accept either one. But you can't say 2 out of 500 here and then 499 out of 500 here. Or you might sit there and say that's 499 out of 500, but binomial experiments, the probability of all the scenarios in the sample space in the binomial experiment has to add up to 1. So if you say this is 2 out of 500, this is 499 out of 500, these don't add up to 1. So that has to go away. I would accept here or here. I'd accept either one. But I won't accept the combination of both of them. It depends on how you look at it and your perspective to it. So your scenarios would be 248 times 1 out of 500 plus a negative 2 out of 499 out of 500. Where the 2 comes in that we're trying to throw in down here, where the 2 comes in that you're trying to throw in down here comes right here. This is where the 2 that you're trying to throw in down here comes into fact. But if you do the 248 and 2 out of 500 plus a negative 2 out of 498 out of 500, I would accept that also. I would accept either of the scenarios, but the 2 that we're trying to throw in, because we bought 2 tickets here, gets thrown in right here. Once again, I would accept either or. But you can't have the combination of one on each. Can't go to, because your probability experiment, you have to add the probability odds up to 1. So the 1, this is a scenario that you have to think of as the raffle, not as the person that's sitting out there saying, I doubled my chances. Okay? All right, the worksheet here, as I've told you, will be a combination of everything that we've done in the chapter. So it's sort of like a review of the ideas that we have talked about. Once again, it will come quickly here, so you need to continue to push yourself. You know, I didn't know that we had the ACT thrown in next week also. So we will adjust as we go along. That's Education 101, being in the school. I'll get you. Being in the school, we adjust. Years ago, when I was a younger teacher, I would really be anxious about that. I don't get anxious about it anymore. We'll take care of it. It will be taken care of. And we'll juggle as we go along. All right, solutions are posted for you in Classroom. And I think I have a set of solutions up here too. I think this is the one. No. I'll print you off some solutions too.